Hi everyone, Christian Aparicio here to give you a tutorial on topology optimization with Nastran Solution 200. So let's go ahead. This is what we plan on doing for this example. We want to take this block of material and essentially let Nastran Solution 200 find what material would be best to trim out. Our goal is to take the mass of 25.6 units of mass and reduce it by 70% until we land at 7.7 units of mass. One thing to keep in mind in this example, we're going to use casting manufacturing constraints. Here on the next slide, perhaps on the next one, or rather I'll give you more details regarding that. Also, we want to impose symmetry constraints. Here we want to make sure that, let me see if I can draw a plane here. We want to make sure that whatever's on one side of the part is mirrored across this plane on the right side. And so I'll walk you through the process of doing that. This is what we plan on covering. I'll briefly describe how this model is loaded. I'll then describe the optimization problem statement. This is the starting point to any optimization. And then I will actually walk you through the process of preparing your BDF file for topology optimization. We will then perform the actual optimization. And then we are going to look at the results at the very end and get our final structure that I showed on the last slide. Just in case you are a professional engineer and want additional training on optimization with Nastran Solution 200, or if you have a general question or would like access to the Nastran Solution 200 web app, my email address is here on the screen. Feel free to send me an email and I will definitely get back to you. Let's go ahead and get started. Here is just basically a snapshot of the model. You can see that on one end, we have a fixed end condition, so this beam is essentially cantilevered. Here on the opposing side, though, we have two loads. One load on this edge is going upwards, whereas the other one is going downwards. So here, as you can expect, it's causing a torsional load on this. And now for our optimization problem statement. Topology is slightly different from size optimization. As an example, instead of defining explicit design variables, we're defining design regions. Here, this whole block is associated to p-solid1. We're going to select this p-solid1 as a design region, and Nastran will perform the optimization on this region alone. Alternatively, if you had multiple p-solids in your part, you can select each p-solid independently to create a design region. So for example, if this block was composed of two p-solids, you could create a design region for this side and then a second design region for the other side. But this isn't the case for this example. We are just dealing with one example or one design region. There are a few things we are doing to the constraints. We want to limit the design region to the following. Number one, we want to define a symmetry constraint. To define mirror symmetry, you first have to define a coordinate system, and here we've defined one, coordinate system 1, with these axes as you can see here. What we want to do is say that the plane represented by YZ, so this axis and this axis will create a plane that kind of looks like this white one here. We want to set this plane as the mirror symmetry plane. And for this, we will be using coordinate system 1. The other thing we want to specify, casting constraint. And I believe on this slide I have an example of why it would necessitate to impose this casting constraint. If we just impose a mirror symmetry plane, you can see here that we would achieve symmetry, but then we would achieve a design that cannot necessarily be manufactured. Once we impose this casting constraint here on the right, we do get symmetry, and in addition, we get something that can be casted. So that would be the second restriction we impose on this design region. So basically we're going to say that the casting direction will be in the Y direction. So that would be here represented by this arrow. And now for the objective, we're going to go ahead and minimize the compliance as much as possible. And for design constraints, we're going to say that the fractional mass should be less than 0.3. Here what the constraint is saying is that we want to retain and keep 30% of the original mass. This is another way of saying that we want to reduce the mass by 70%. Towards the end of the presentation, I will go into some commonly asked questions. I'll go and describe what the design variables are. I'll describe what compliance is, what fractional mass is, and then I'll describe how to create the plots at the end where you remove the actual elements. So make sure to stick around at the end of the tutorial for that. And now we are done summarizing our problem statement, so let's go ahead and move on. Again, if you have any questions or comments, my email is here at the bottom of the screen. Feel free to send me an email if you do have a question. So what are the explicit steps we will be taking for Nastran? I have provided a PDF file in the video description below. Feel free to download that PDF file and follow along. I will also show you how to create your design regions, your objective, and your constraints. We will be using the Solution 200 web app for this. We will then perform the optimization with Nastran, and then we will go ahead and look at the results in the F06 file and Patran to view the actual topology region. So let's go ahead and get started. Again, we will be using the Solution 200 web app. Essentially lets you take a BDF file that might be Solution 101, 103, or any other 100 series BDF file. And it lets you create your design variables, your objective, and your constraints. And then at the end, you get a Solution 200 BDF file, which can then be submitted to Nastran for optimization. So let's go ahead and actually get started with this. And the first thing we'll do is go to the Nastran Solution 200 web app. Again, this is available if you send me an email. And my email address was shown earlier in the video presentation. The first thing you want to do is navigate to the Topology web app. Right now you can see in the top left-hand corner, it's currently the size optimization web app. If you, here in the top right-hand corner, if you go to Topology Optimization, this opens a new window. It is in this window where you can access the topology capability of the web app. So make sure it says topology in the top left-hand corner. Now, on my desktop is the original file we are starting off with. Here I have Patran open, so let me go ahead and show you that. So this is the block we will be focusing on. Again, one end is fixed. The other end is where we are applying our loads. It's hard to see here. Maybe if I hide the mesh for a moment. Actually, let me make this wireframe. You can see on one side, we've defined our coordinate system here. This is necessary to define our casting direction and our mirror symmetry plane. So moving on from there, on my desktop is the BDF file that was created by the pre-post processor Patran. This again is a summary of the entire finite element model. It describes the materials, of the elements, of the locations of the nodes. Everything about the finite element model is inside of this BDF file. So now what we can do with this is import it to this Nastran Solution 200 web app. So let's go ahead and take some time to do that. And the web app will identify all the p-solids, all the other properties that can be set as design regions. Here you can see that p-solid 1 is the only design region that is available. So what I can do here is click on the plus icon to reserve it as a design region. On the next step is our newly created design region. If you click under options, this is where you can specify your symmetry constraints and your casting constraints. So make sure you've selected these two checkboxes. Just in case if the columns are too tight for you, you can also check expand width of table, and this will better help you read what's here on display. Now let's go ahead and define our symmetry constraints. Here under the use symmetry constraints, change this to yes, because yes, we want to define a symmetry constraint. For the coordinate system ID, use the ID that you see defined in Patran. Here you can see the ID is 1, so we'll go ahead and set this first box to coordinate system 1. And the symmetry plane, we want to set the ZY plane of the coordinate system as the symmetry plane. So ZY or YZ, so let's go ahead and mark that checkbox. And then we can move on to defining our casting constraints. Here, yes, we do want to set this as a constraint, and the draw direction will be in the Y direction. So again, this is the Y of the coordinate system. And then the dot option should be single and set no for this last column. Here on the right, you have the outputs. The top bar entry is what defines this design region. At this point, you're done configuring the variables, so we can continue on to the next section, which is defining our objective. The objective, or rather, when you switch to the objective, a constraint, or rather an objective, is automatically created for you. Here, the compliance or the work done on the part is set as the objective. We want to minimize the compliance as much as possible. Again, towards the end of the presentation, I go into more detail regarding what is compliance and a few other details, so definitely stick around for that. We're done setting our objective. Let's go ahead and define our constraints. Here, a fractional mass constraint is created for you automatically. Right now it's set to 10% or 0.10. What we want to do in this example, we want to make sure that the mass of the final solution is 30%, or rather we want to reduce the mass by 70%. So here to specify that, you would type in 0.3. It's very important that you include the decimal point. Again, this is fractional mass, not percentage, so always include the decimal point. Here we say we want to keep 30% of the original mass. Another way is to say we want to trim out 70% of the mass. So now moving on, let's go ahead and configure our settings. Here in the top right hand corner, this is where you can modify a lot of the settings for the optimization. Here the des max parameter specifies the maximum number of design cycles. Here instead of 50, we want to set this to 100. And now let's go to the exporter. Here you can see that the web app has done a number of things. Here on the right is the original BDF file. It's a solution 101 BDF file. But now here on the left, the BDF file is solution 200. And it's included other statements such as the analysis, the objective pointer, and the design constraint pointer. Here on the right, you have entries for the design region, the compliance objective, the constraints for the FR mass, and the parameters for the optimization settings. Now what we can do is download both of these files. And here they've been downloaded to my downloads directory. And now I can go ahead and start Nastran and select the model BDF file to start our optimization. This optimization goes fairly quick. I believe it takes a little less than 2 minutes. So right now I'll just go ahead and pause, and then I will continue once the optimization is complete. The optimization has finished, so let's go ahead and confirm if the optimization went through successfully. Open the F06 file inside of Notepad and then scroll to the very bottom. Or before that, it's always a good practice to search the file for a user fatal message. And here I can see that the message is absent, so that is a good indication. And now let's go to the very bottom and look here. Towards the end, you find the section called the Summary of Design Cycle History. After that section, you find this message, run terminated due to hard convergence. This message is indicating that the optimization went through successfully. If you see some other message, that means the optimization behaved differently. Now that we know that the optimization went through successfully, let's go ahead and view the topology solution inside of Patran rather. So for this, let me go ahead and close this old database. And let me show you how to bring this into Patran. So let me go ahead and delete some files here, and then I'll go ahead and create a folder called 0pat. And then here I'll start my new Patran session. And again, just in case you have any questions or comments, if you're a professional engineer and want more training, if you want access to the Nastran Solution 200 web app, you can contact me at this email address. If you are a student, you can also get access to the web app. Just send me an email and I will definitely get back to you. Now let's go ahead and open Patran. Here's my new Patran session. Here in the top left hand corner, if you want to create a new session, just click the new icon and give it a name and click OK. And now let's go ahead and import the model PDF file that was exported by the web app. So here I'll click on model PDF and click apply. This will bring in the cantilever beam. So let's go ahead and zoom out of this for a moment. And now let's look at the topology results. So to do this, go to Tools, then go to Design Study and click on Post Process. Here on the right hand side, you have a new form. Click on Select Results File. Go to the same directory where your optimization was performed. And here, let me actually show you that directory. You have a bunch of new files created. The one file you would need is the model.des file, so DES. This file is what we can select in Patran. Click OK here and click Apply. Here you'll see Patran react to that. And now if you go to Action, Display Results here in the right hand corner, select this one row, Design Cycle 55. Set the threshold to 0.4. I will mention what threshold is later on. Then click apply. And here is my final result of the topology optimization. So first off, you can see we have symmetry here if we look at it from the top. Also, we can see that this part can be manufactured. It honors that casting constraint we specify for this design region. One last thing I want to show you, just in case you want to see the original part, you can just here on the left hand side or before that, click on the model tree that you see here almost at the center top. Here, just uncheck box the items and then you can sort through the various groups with the various parts. The default group is what has the original part, and then this group named high dense group, that's what has your topology solution. So that's how you perform a topology optimization with Nastran Solution 200. At this point, that's the end of the tutorial. But now there are some slides I want to go over. I know when I started working with topology optimization, some of the terminology was a little foreign to me. I didn't quite understand it at the beginning, but hopefully with these few slides, I'll save you some time in understanding some of the concepts. So now I'll go ahead and take some time to go through these things. The first question you might have is, what are the design variables in topology optimization? remember that at the very beginning of this presentation, we just said that this P solid 1 is the design region. What Nastran does internally, it assigns each element, and here I'll just pick some arbitrary element that I'll call xi, where I is the element. It'll create a design variable for each element that corresponds to what's called the normalized material density. So here's an example. Let's suppose we set the design variable to some density, and this is the material density of the element divided by the original density of the entire part. So suppose we had a density of 7,800 kilograms per meter cubed. And let's suppose that the design variable was 50 or 0.5. That means this density would be half of 7,800. So that would be about, I'm having some hard time doing the math right now. Here, just to save myself the trouble of doing this simple exercise, take half of 7,800, put it here, and then this would give you the value of 0.5. Each element would have its own density, Pi, and this is what happens. You set the design region, and then a different design variable is created for each element that corresponds to this normalized material density. Densities that are close to zero, so here if you look on the spectrum, close to zero, is almost as if that element is not participating at all in the topology solution. So here you can see every element that is in white has a density close to zero. So in essence, this element can be discarded, it can be disregarded from the final topology solution. Design variables that are close to 1, on the other hand, so that's the top of the spectrum, these can be considered critical for the solution. So these elements that you see here that are high in depth of color, you should keep these elements in your solution. So here, keep. Now let's go ahead and talk about the next question. What is compliance? If you go through the documentation of the Nastran user guide, it has the same definition. Compliance is the product of the load times the displacement, and it's repeated again in the guide. If you recall back to your undergrad engineering courses, the work is defined as the product of the load and the displacement. This is actually related to the total strain energy in the object. So here you can see I have strain energy at the bottom. You can see it's 1/2 the product of load times the displacement. So if we set the objective to minimize the compliance, what we are doing is we are minimizing the work that is occurring in the part. And this is comparable to saying that we are minimizing the strain energy in the part. Now, if you need further proof that this is what's happening, if you open the F06 file and you look for the section called element strain energies, there's one line that gives you the total strain energy in the part. So here you can see that it's about 9,000 here. Remember, the strain energy is half the work. So if you double the strain energy here, you should have a work or compliance of 18,000. So let's go ahead and mark that here. So here we've doubled the strain energy. Here, if you look at your summary of design cycle history, this column for objective are the values for the compliance. And here you can see that after we double the strain energy, we have the work done on the part. So this, or rather, just to sum it up, compliance is the work done on the part. One question you might be asking yourself is, how is it possible to increase the stiffness of the part if we are using the same material? By increasing the stiffness, I mean minimizing the work and the strain energy in the part. So how exactly are we able to increase the stiffness of this part? Before I go into details with that, I first have to define what a fractional mass is. Here in this first box that you see here, this could be defined as the original mass. So I'll call this original. Let's suppose we set the fractional mass constraint to be less than 0.75. What this means is that the solution should keep up to 75% of the original mass. So here you can imagine that 25% was essentially removed from the solution. The same for FR mass less than 0.5. That means that half of the mass has been removed, or half the mass was retained. This is important for the next slide. So remember that each element in topology optimization is getting a design variable xi that represents the normalized density. Now, remember that the constraint for this example on fractional mass was 0.3. So here I believe it was R1 was the label, was less than 0.3. What Nastran does at the very beginning of the optimization, it will set all of the design variables to 0.3. So here, 0.3 here on the screen. Remember that this is equal to Pi, or the density of the element, divided by density original. So now, at the very beginning of the topology optimization, it starts off with material densities less than the original density. So here, if the density was 1000, that means the density of this one element and all the other elements will start off at 300. So here, at the very beginning of the optimization, the fractional mass is 0.3. That means that 30% of the mass was retained. Think of the original design starting off as handicap. So here we'll go ahead and write handicapped here. Now, since we reduced the density and the mass of this structure, that means we've actually increased the compliance or the work done. So here I'll write C has been increased. And that's because we've handicapped, or we've reduced the density of the material in the elements here for the initial design. So now the objective becomes minimize the compliance, and what the optimizer will do, it will vary each design variable xi. It's going to make some of the design variables very small. It's going to make other design variables very high. Now here, if we look very closely at the diagram on the right, here I just have a marker plot of the design variables, or the normalized material densities for each element. You can see here that some of the densities for some of the elements are very, very small, almost a point on the screen. This is the same as saying this element, this piece of material, has little impact on the stiffness of the structure. Other design variables, or normalized material densities, are increased. So here are these larger circles that you see on the screen. These are critical for the stiffness of the design. So that's how it's possible to increase the stiffness. First, the mass is handicapped compared to the original. This causes the compliance to increase. There's a loss of stiffness there. But then as we minimize the compliance, which is the same as increasing the stiffness, the various design variables are sized differently to eventually get to the optimized design that you see here on the right. Just in case this is still coming across sort of confusing, I will repeat this discussion on the other topology optimization tutorials, so feel free to watch those if you want further details on this. Now the last thing. So with topology optimization, The optimizer is not actually removing elements. It's assigning scores, if you will, to each element. Again, the scores xi are the normalized material densities. If you have a score close to 0, that means that element is not necessary. Whereas if you have a score or normalized material density close to 1, that means you should definitely keep elements close to this. Now, what we did in Patran, we utilized this tool with the threshold value. So here you can see that we set the threshold value of 0.4. What this is saying, it's drawing a line in the spectrum. So here, what we're saying is everything above a 0.4, anything with a score or normalized material density of 0.4, you should keep that. And this is what was shown here in purple. This is the final solution. Sometimes, just in case 0.4 isn't enough, sometimes you can also use 0.3. Generally, you want to use the threshold greater than 0.3 or 0.4. Let's see, what else do I want to say? So again, the optimizer is not actually removing elements. It's assigning these scores to each element, and then it's up to you to decide which elements you want to screen out. So that's the end of the tutorial. Again, if you're a professional engineer, you have questions, you want additional training, you can contact me at this email address on the center of the screen. If you are a student or if you are a professional engineer and want access to the Nastran Solution 200 web app, you can also send me an email for requesting access, and I will definitely work with you. And then again, I have other topology optimization tutorials, either on my homepage or the YouTube channel I have. There I will go over other versions of these slides just in case you want more details with that. With that, thank you for watching, and I'll see you in the next video.